This is what happens when we ignore value of z less than or equal to 0. What is actually going on here? Why do we get all these glitches? Let's take a look at our 3D to 2D projection formula. Do you see the problem here? What happens if z become equal to 0? We end up dividing by 0, and division by 0 is undefined. You may think we could just replace z with some very small value close to 0. But that doesn't really solve the problem either. To understand why, let's look at much simple function, 1 divided by z. What happens when z gets smaller and smaller? As z approaches 0, the value shoots toward infinity. And because our projection formula also divides by z, our projected coordinate explodes toward infinity as well. That's why triangles suddenly stretch across the entire screen. Trying to fix this by clamping z to something like 0.1 creates a different problem. We are modifying z, but not changing x and y accordingly. That's changed the shape of the triangle itself. The angles become distorted. It also completely breaks texture mapping. The distance between points change, but the UV coordinates stay the same, so interpolation no longer matches the geometry. Now, let's look at what happens when z approaches 0 from the negative side. The same thing happens. The values still go toward infinity, but now the result becomes negative. Negative z value produces mirrored coordinates. The image projection behind the camera becomes inverted on both x and y axes. If all three verticals of a triangle have negative z values, we can simply discard the triangle. But what happens if only some verticals are behind the camera? If we discard the entire triangle whenever any point has z less than or equal to 0, this is what we get. Technically, this avoids glitches, but visually, it looks terrible. Triangles pop in and out of an existence the moment they cross the camera plane. How do we fix this problem? We introduce a clipping plane, usually called the near plane. Notice that we are not clipping at z equal to 0. We clip slightly in front of the camera instead. And for demonstration, I can move this near plane much further away from the camera. Now you can clearly see what clipping actually does. Everything in front of this plane is cut away, almost like slicing the world with an invisible knife. And this creates another interesting problem. Sometimes in game, when the camera gets too close to a wall or an object, you can suddenly see inside it. That happens because the near clipping plane is literally cutting the geometry apart. The renderer only sees the part behind the clipping plane, so the inside of the object suddenly becomes visible. We can think about clipping as a simple 2D problem. Take a look at this example. Notice something interesting? When we slice a triangle against the clipping plane, we can end up with a 4-sided polygon. The important thing is we are not deleting triangles, we are reshaping them. That means clipping can actually generate new geometry. Instead of one triangle, we may end up with 2. This means additional work during rendering. And if we allocate memory every frame for these new triangles, performance can drop significantly. We will solve the allocation problem in a separate video, where I will show the custom memory manager I use in my renderer. But for now, let's focus on clipping itself. We iterate over every edge of a triangle. If the point z value is greater than the clipping plane z, the point is visible, so we add it to the results. Next we check whether the edge crossed the clipping plane. If one point is in front of the plane and the other one is behind it, the edge crossed the clipping plane. In that case, we calculate the intersection point between the edge and the clipping plane, and add that point to the result as well. Then we move to the next edge and repeat the process. After processing all edges, the result polygon will contain either 3 or 4 points. If we have 3 points, we output one triangle. If we have 4 points, we split the polygon into 2 triangles. Triangle 1, points 0, 1 and 2. Triangle 2, points 0, 2 and 3. So how do we calculate the intersection point with the z clipping plane? Fortunately, this is very simple. Because the clipping plane is parallel to the x and y axis, we only need to work with the z values. First, we calculate the z distance between the start and end point of the edge. Then, we calculate the distance from the start point to the clipping plane. Using those two values, we compute a ratio that tells us how far along the edge the intersection happened. That ratio can then be used to interpolate everything else: x and y coordinates, texture UVs, colors, normals, or any other per vertex data. This ensures the newly generated vertex matches the original geometry perfectly. Now, basically all we have to do is repeat this process for every triangle. Modern GPUs still do clipping internally. Even today, this is a fundamental part of the graphic pipeline. And this tiny piece of math is what stops 3D worlds from tearing themselves apart the moment they touch the camera.